So hi, my name is Pradeep Verma. I am going to explain 2D NPN vertical bipolar transistor using Sentaurus TCAD, and we will use Sprocess for the designing this transistor. Like we are going to use fabrication processes like deposition, photolithography, implantation, diffusion, and these steps will create the parts of the transistors. So that is called S process. And I have three more videos on this Sentaurus TCAD, an overview, and ST and SWB. So those videos is essential for you to first watch those videos, then you will be able to understand the workbench environments, then like how you can work in that interface. So first of all, let's log in our account. So for that you have to go to terminals, then you must have your ID like this, ss space -x your ID, like in my case my name is my ID Pradeep @172.20.4.50, I think it is 57, right, for Sentaurus TCAD. So just press enter and use your password, and then hit the enter button. Then after that you have to base it, use the command base, then you have to source it like the term directory, like you have to type source, it's a small s, then space hyphen linux underscore new scripts synopsys 2025, then hit the enter button. After that you have to open SWB workbench where we are going to work today in this video. Now it is being opened. So you can see this is the SWB workbench where we will be working. So by the interface of this, for the interface introduction, I have made separate video, and I may have been shared with you guys that video also. So that is must, you should watch that video first, then come to this part. So let's begin our designing of NPN transistors. First of all, you have to log into your directory. You have to attach your directory, working directory. So for that purpose, just click in the space, right click in this area, and then folder, then attach root. Then just click OK, then you will come to your directory. Like in my case, my directory, working directory is staff Pradeep. So in that there is a db directory made. In this db file I have made different folders for my device simulations, right? So like I have earlier make a folder to the name of Sprocess. So let's make it to let's make how you can create your own folder in this db directory. For that, for the creating, you have to click right in this free space, then come to folder, then new folder. Let's rename it Sprocess test. So I am going to name it Sprocess underscore test, right? Give it a name, or I can name it like NPN transistor, right? NPN underscore transistor. Okay, that's it. And then after giving an input, after giving the file name, you have to press enter. Yeah, by this way we can create a folder in the working directory. Now we have a folder with the name Sprocess NPN transistor, but there is no any file in it. So how to get that? So for that purpose we need to create a new file here, create new project, then come to traditional project, then it error message will pop up. Then just click OK, and you have to come to this directory where you have clicked, and then go, and then you just went to for the creating a new file. So for that you have to come in your own directory. This, by this way you can go, like in my case it is staff Pradeep. Maybe in your case your directory is in project folder, so you have to click projects, but in my case it is in staff. So I will double click on staff, then I have to select my folder. Like here I have mine with my name Pradeep, so double click on it, then db, then this folder just we have created now, right? Sprocess NPN transistors, then double click on this. Now after reaching this folder you have to click OK. So now we have a page opened here. You can see here, this is Sprocess NPN transistor glocal the .tmt file. There is a tmt file we have just now created in NPN Sprocess NPN transistors. After this we need to add a tool for the device making, like we are going to make it through process. So we need to add Sprocess tool. Like here you can see Sprocess. I may consider now you have seen my earlier videos, though then you must know about these SDE, SDevice tools, and SVisual also. So in my for making the transistor using Sprocess, just we need this tool Sprocess. Select Sprocess, OK, and select batch mode. Batch mode in the sense it will run in the whole code in a single run, like that. So interactive in the sense it will run line by line. So good thing is to go with batch mode, right? Just click OK, and a tool will be here. Now what? We have the tool, but when you go through the edit input and command lines, you will find that there is a empty file naming with sprocess fes.cmd. So there must, here in this section, in this fes.cmd file, we are going to write our code so that our device can be made. So all the fabrication steps one by one we are going to assign it. So let's take an example file and show you how we can do this. So I'm going to open getting started here, and then in there may be Sprocess. Yeah, these are the SD device you may know as you have seen my earlier videos. Now come to Sprocess. Our working area is this, like, so I want to illustrate 2D GS, right? 2D GS. So I will double click on it, and it will like we have changed some changes, we have done some changes in our folder, right? We have added tools, so for the sake we have to save it. That's why this message came. So just click on save button, and it will ask to save again. So just okay, let's do double click on this file, and then OK. Now it is saved, and 2D GS file we have opened, right? So let's see what is the input files for these processes. So just click on this tool and right click and edit commands. Then you will see, like this is a 2D and MOSFET, right? 0.18 micrometer technology. What do you mean by 0.18 micrometer technology? It means that this is the like channel length. I hope so. This is the thing, means minimum length of the channel. That is the, I think, known as technology in MOSFET cases. If I'm wrong, then correct me in the comment sections. And yeah, but I want NPN transistor file, not the MOSFETs. So let's close it and look for the second tool. What is the input file for this example? So I am going to again same way edit input commands. Then here we can see we have the 2D NPN vertical bipolar transistors. This is the file we want to run and understand the whole process for fabricating the NPN transistors. So what I am going to do, I just want this code in our folder, so I will just select all this file and copy it. So just Control A and Control C, then come to our folder like this. You can see this is our file, Sprocess NPN transistor G localhost. This is our file name. So I am going to paste this code in this file .cmd file. So Control V. So let's save it and just close this another folder and come back to your own folder. So just double click on this folder. Okay, here we can see we have our tmt file and we came to our folder. Like you can verify from here, Sprocess NPN transistor G localhost this .tmp, right? Let's close this one and again let's see in our tool input file is there or not. So for that, just click on it, right click into edit input commands, and we can see now we have the input file in our tool. So after explaining before explaining these whole command lines to you, first I would like to run this simulation first, and after running I will illustrate these codes along with the simulated files, so that you can see or visualize, you can understand in a much better way. So for that I am going to select this node. You can save it from here, right? Just select this node and click on run button, right? Just go with that, and it will take I think 5 to 6 minute time for the running the whole process, and so that we need to wait till then. So during the simulation you can see a lot of process being held, like being solved. Like you can see here species, phosphorus, dataset, and like anil step time, 300 minute temperature, like this ramp rate. And if I go up, then there may be something that is good, like you can see diffusion mechanics, then diffusion. So like diffusion process is being solved at that moment, and for the antimony it is being solved, means our device is being solved, being fabricated. So it will take 5 minute time, 5 to 6 minutes. So let's wait and let's look out the output file of this command also. So you can see here these are the codes we have given here in our fps.cmd file. We have like defined line x, line y. What do you mean by line x? Means line x means it will parallel to the x-axis, right? And y line means parallel to the y-axis, right? So line x, in the sense we are defining the location. So location is like 4, so it will go in the y directions, like 4 will be obtained in the y direction. I will show you while the simulation is run completed. That will be better way to visualize the thing, the code. I hope. Yeah, still it is running. It will take some more time. Till then I have to wait. Let's wait. So it is done now. Our simulation is done. You can see yellow color is being appeared. It means done. Let's look the output file for this. So we have different like you can see buried PLX, final PLX, and here sinker PLX. Then we have different TDR file, like npn1fps.tdr, npn2.tdr3.tdr4.tdr5.tdr. So these outputs we have just defined in our command files. This is the command files, and we have defined these output, like you can see here npn1, right, struct tdr npn1. Then we have another here like structure tdr npn2. Then we have another npn3, similar way 4, and in the last 5. So these are the output files we have saved after some processes. Like if I tell you, like npn, we have just created a buried layer in our material, and then after that we created a epitaxial layer in our material. Then after this process we are going to save our device using this name, node vertical npn1. So what it will do, it will save this process, like till now the process, the fabrication process we have performed, like buried layer and epitaxial layer growth performance. So we have done this process till now. So these processes will be saved in this file. Then after we are doing some like sinker we are going to perform. So here we are going to deposit material, then photolithography, implantation we are going to do. So in this folder like npn2, these whole processes, means including these whole processes, will be going to save. I mean this whole process will be going to save sinker and this. Then after we are going to form the base region. For base region we are going to do photolithography, implantation, diffusion. So this process will be going to save in npn3. And emitter, in the final we are going to, for the emitter we are again going to do photolithography, implantation and diffusion process, and it will save the results in npn4. In the final we are going to do some backend etch, material oxide, and some deposition and etching. So these things will be going to, means whole the process will be going to save in npm file. Means once again I would like to illustrate like the whole thing, like meshing part, these grid formation, these masks thing, and this buried layer formation, epitaxial layer formation is going to save in npn. After that we are performing some another fabrication processes and saving it in this file. So whole process till now will be going to save in this. We can visualize it. Let's visualize it so that we can understand. Let's I want to open npn2 fps.tdr. So you can double click on it and it will open, or you can just single click and launch, press launch. So we can see here this is npn2 fps till now. If I again open this folder, so here we can see for npn2 fps tdr, if I go here we can see, right, vertical npn2 node 1. So till now we have performed some implantation, like deposition of oxide material and sinker formation, and again deposition of silicon, arsenic concentration, deposition of material, buried layer formation, and epitaxial layer formation, right. So I think this is the buried layer formation in the silicon region, and this is the sinker we have performed here, right. So npn2 is showing the result till this process, right. If I am going to see npn3, then it will show in all these processes including this base formation. So let's see again and visualize it. npn3, just click on it, then press launch, and it will show you some extra thing. You can see n1 vertical npn3 fps.tdr, and our file have just made a base region, right. Here you can see base formation. and we have another 2 TDR. Let's visualize it also. NPN4 launch. This is the, here we have just created in 4, in case of 4 we have created a emitter region, right? And this one is the emitter, this one is base, this one is collector, right? So emitter, base, collector. And in the final, let's see what happened in the final. For that final we have to create NPN5 FPS TDR launch, and now we can see there are some material deposited in these region also. If I want to whole screen, then just come to in this, maximize it, and we can see. Now again press the, like till now like in NPN4 we have just have emitter, base and collector, but now we have the some contact material also that is defined here. Like we can see deposit material aluminum and is the rest material, means first they have deposited all over the region aluminum material, then using the mask, metal mask, they have patterned it for the that specific region where the contact should be made, like for the emitter, for the base region, and for the oxide collector region. You can see these black dots, right? If I zoom it, then we can visualize these oxide blocks are just for the passivation, you can say. Like here we have the base and emitter in besides, so there must be some like passivation. So for that and we have deposited all over the oxide layer, oxide thin layer, and then patterned in so that we can make the contact for it. So all these whole processes are in this this one is the oxide, this one is the metal aluminum, this is the emitter, this is the base, and you can see this one is the collector. So all these whole processes has been instructed in this fps.tcmd file. So after visualizing these things, now we will try to understand each line of this code. So for that I need a break, so let's pause record. So let's again see the structure and structure of the 2D NPN vertical bipolar transistors. Like this is a 2D dimensional structures, two-dimensional structure, right? NPN. So where is N? It's N, P, and again N. Vertical, why it is called vertical? Like you can see topmost is emitter here, and then after that it is base region, then collector. So it is like top to bottom approach, that's why it is being vertical, and it is a bipolar transistor, right? So initially what we are doing, we are going to do in the command section, we are going to form a silicon region with p-type boron doping 1E15 concentration that forms the starting substrate. Then we are going to use a standard material like silicon dioxide, like this whole region is silicon. Then we have some oxide region, you can see here, like this one is oxide, and some aluminum material, like these materials are aluminum, and we have used some dopants like arsenic, antimony, phosphorus, boron doping for the doping purposes. So these are the materials are being used in the S process. Then after we can see there is a one P region, this one is the P region, which is sandwiched between two N region, that's why it is being called NPN, that is emitter, base, collector, right? So and it is a vertical geometry. So now we are going to perform the fabrication steps. So let's see our command line files. So as we can see, they have given this .cmd file a name 2D NPN vertical bipolar transistor. Hash means this is commented, this is not going to be simulated in the file. So for commenting any line we just use hashtag, right? So these are commented, just a name thing. Now next move on to line X location this, right? So here we have seen different lines, we have line X, line Y, right? Line X, line Y, and these lines have some location like location 4, location 5, location 18, location 30, and these lines have some spacings also. Then they have some name like tag, they have subtop, just like line X, that is at location 4 it has a tag name with subtop. Similarly in line X location 6, this line has a tag name of sub bottom, and the similar way line Y has sub left, and at location 30 tag is sub right. So where it can be seen, so let's visualize it first. So if I open it simultaneously right here, so just a little bit, yeah, now it is fine. So let's understand these line, like line X location 4. So where is the 4? Like in the x-axis we can see our device is from 0 to 6, and in the y direction it is from extend to 0 to 30 micron, right? So line X location 4, so this is the line X, and at location 4 I think if I zoom it a little bit, so we can see the line 4. You can see here, this is just the line location X4, and it has a spacing of 0.1 micron, and that is tagged as subtop. So this location is tagged as subtop. In line X location 5, that is here, right here, spacing is 0.1, that is this spacing is like the difference between two lines basically. So meshing will be created according these spacings, right? And line 6, its spacing is like line 6 if you want to visualize this here. So this is like 0.7 micron tag sub bottom, and this position is known as like they have mentioned it is substrate bottom, and this is like substrate top, right? This location is substrate top, this location is substrate bottom, means this region 4 to 6 is just a substrate, and other things we will look into it. So let's see the line Y. So here line Y location 0, that is this point. If you zoom out, so you can see this is the 0 position, and this is the line Y. At this position the spacing is 6 micron, right? And it is tagged with sub left, means substrate left, right? It is the 0 at 0 location, it is substrate left. At the right it is like at 30 micron. At the end of right it is named as tag as sub right, and its spacing is like 0.50 micron. And at 18 location, like if I zoom it here, at this point the spacing is 6 micron, and 18.5 it is like 0.5, and 30 it is 0.50. So why the spacing is being changed according at different spacing at different location, the spacing is different. So basically what we are doing, we are just creating the mesh where we are creating the finer mesh where the physics will be solved. Let's see, this is the active region, right? Here mesh should be finer so that physics can be included. That's why, like in this case also, at the 4 position location 4, we created a fine mesh like 0.1 spacing, but when we came to 6 we just created coarse mesh like 0.7 spacing, right? And our device approach is top to bottom, means vertical. That's why we are doing finer meshing in X line instead of Y location, Y line, right? You can see in here a lot of spacing are there, correct? So this is the basic meshing strategy, and this is the basic structure of our device. Then after that we are they have used global mesh thing, like this is the commented one, global mesh settings for automatic meshing in newly generated layers. Next is like grid, set normal growth ratio 2D 1.1, set minimum normal size 50 nanometer, means the minimum normal mesh size can be 50 nanometers. So you can see here these are in micron, right? So if we convert it in nano, so it will be like 500 500, yeah, this one 6,000 maybe, yeah, 6,000, 100 and 700. So none of these values are less than 50 nanometer, right? So this is the set, like we have defined a spacing, and those values are greater than this global minimum size mesh size of 50 nanometer. So that's the thing, that is the purpose of making a grid file using these commands. Then they have used mgoals accuracy to E-5. And if you want more about these command lines, so you can just go to the help section, then manuals, then you can come to Sprocess. Then here you can search your keywords, like their G goals or their M goals were there, right? If I see, yeah, M goals, so just search it here, M goals, and certainly you should have something. Okay, let's search another keyword like grid. If we search grid, is there anything about grid? GRID, no. Why? Oh, sorry, I am searching in wrong thing. Here we need to search here, right? GM goals, GOALS, yeah. So you can see here it at 850 they have defined the M goals, and go through these commands if you want to understand more about things. Similarly, we can search grids, like if I'm not wrong, then they must have said something like this, extract grids, so about those things, right? Here's M goals and those things are here, right? So likewise we can explore these commands also. So let's see what is the next. Like here you can see define layout mask. So as we know, while fabricating any device, we need multiple of masks for different process, different fabrication steps, right? So for that purpose they have defined the mask. Like here if you go through these commented lines, they have mentioned like n-type emitter is also used as contact to molecular. Masks are listed in order to they are used, means these marks are in a order in which they have used for fabricating the device. Mask for front end processing and mask for back end processing. So like they are defining here the mask name sinker segments, and it is in syntax negative, right? Negative syntax. What does this line represents to us? Let's explore this first. So see, sinker, where it is, where the sinker is. So if I just tell you, just show you, this is the sinker, right? And this region is going to expose, or you can be this region will be performed using the mask name with sinker. here you can go sinker, right? And it is from segments. They have defined the segments -1 to 22, then 24 to 35. What is the meaning of negative here? I will tell you. So they are going from -1 to 22. So this till this it is 0. If you come this axis like left side of this 0, then it will be negative. So from here -1 to 22, somewhere here, right? If I zoom it a little bit more, okay, let's zoom it using this. Oh, it's too much. Yeah, here, right? So till here 22, 25, 22, here, somewhere here, right? Till here. So they have defined the mask from -1 to 22 somewhere here, and then after 24, so it is 25, so somewhere here it will be 24, right? So from 24 means somewhere here to 35, right? Till here. So the negative thing is telling that between these regions, between 22 to 24, the mask will be opened, means that region will be open, and otherwise from -1 to 22, that there will be a segment. -1 to 22, there will be a segment. We closes the whole regions, cover the whole region without any gap, right? And from 24 to 35, same thing will be happen here also. There will be no gap, no all region will be covered. So using this sinker mask, we can deposit only this region, like in between 22 to 24 region. That is the purpose of a mask, designing of a mask. And negative things tells in between these the region is opened, right? So this is the sinker mask that is defined for this region implantations, right? It's for the base region. So where is the base? Here you can say this region. I have told you that this one is the base region. So for that region also they have a mask that is segments from -1 to 1.5. It is also from starting from somewhere -1 to 1.5, right? So 1.5 maybe somewhere here. If I zoom it, so right somewhere here, right? So you can see somewhere here -1 to 1.5, there is, means this is the end point of this base, right? So -1 to 1.5 till here, and then after 13 to 35, right? So somewhere here it is 13. So you can see this is the section 13, that is here 13 to 35, right? So from here 13 to 35 it is all over covered, right? And from -1 to 1.5 it is covered, and this total region is opened. So this means this region is going to be exposed, means the purpose of making the mask is completed, right? Negative word is used so that this region tells that this is open. In between these coordinates, in between these two segments, this region is open. Negative things tells that. So we have a sinker for this collector region, we have a base mask for this base region, and now similar way they have designed a emitter mask with using these segments. So let's explore these segments also, like -1 to 2.5 somewhere here. This is the 2.5 values, and 8 to 22, right? So somewhere here I think 8. Okay, let's yeah, here, from here, right? So somewhere here 8 to 22, from till the here it is covered. 1 to 2.5 it is covered, then 8 to 22 it is covered, then 24 to 35 it is covered, means the gap is in between 2.5 and 8. So the gap is in between 2.5, that is the point of 2.5, and this is the point of 8. So in between this is the gap, that will be the emitter sections, and next gap is 22 to 24, right? 22 to, that is somewhere here, 24, again they have the gap, that is somewhere here, right? This is the gap, right? 24 to 24. So you can see if I can zoom it, like, yeah, here. Okay, so the third one was 2.5, that is this value, to 8 there is a gap. So 2.5 from starting from here to 8, this gap for the emitter region, right? Okay, next gap is 22 to 24, right? 22 to 24, here you can see 22 to 24, there is a gap, right, for this collector region. So using these two marks, three masks, we can do the fabrication steps, right? And these masks are known as front end processing mask, for front end processing. And we have two more masks for the back end processing, like mask name, that is contact segments, then mask name metal segments. So basically these like mask for back end processing, in the sense, after the fabricating this whole device, like after creating the emitter, base and collector regions, and these buried layers also, we need to make a contact for the device. So for that purpose they have created another mask, like mask name contact segments, means it is starting from -1 to 3.5, -1 somewhere here to 3.5, right? Let's explore this 3.5. So somewhere here, right? See, this value is 3.5 here. So -1 to 3.5 somewhere here, and after that 7 to 10 somewhere, if I zoom out and then create this is the whole, this is the point of 7, and to 10 here you can see they have another, like 8 to 9. Okay, 7 to 10, yeah, 7 to 10 they have for this layer. And similar way they have designed this mask for the contact formation, and after depositing the material in these regions, they are going to expose using the metal mask for this metal contact formation. Means they are going to deposit all over the aluminum material, and after using the mask, they are going to etch it for the precise contact, or for the contacts, right? So this is the whole thing. And after making the mask, now they are going to define the region, like the region is to be silicon. The region is silicon, like x low is subtop, like we have defined that x low is substrate top. Somewhere here we have said that at 4 sub top is there. X high is sub bottom, right? At 6 we have said that it is substrate bottom. Y low is substrate left, yeah, we have denoted like at location 0 it is known as sub left. substrate left, and y high it is substrate right. So from 4 to 6 whole region is made with silicon, and initial concentration of this region is 1E15 per centimeter cube with filled with boron. Means its dopants are boron is being used for the initial concentration, right? So this is the substrate definition in the device for NPN transistors, and they are using advanced calibration. Now after this they are going to use a buried layer, right? So deposit material oxide type isotropic, time 1, rate 0.25, right? So this is, now they are going to deposit a oxide material all over the substrate, like top of the substrate. Here they are going to deposit oxide material, and they are going to perform it for 1 minute at the rate of 0.025, right? So using these time and rate, they are going to achieve a specific thickness of the oxide layer. After depositing the oxide layer using these commands, they are going to implant antimony implantation, right? So dose is 1.5E15 per centimeter square. They are taking the dose, and with 100 kilo electron volt they are going to perform the implantation of antimony in this area into the deposited oxide. After doing the implantation, they are going to etch the deposited oxide on the top of the surface. So etch material oxide, type anisotropic, time and rate. So these things, rate and time, will decide how much thickness to be etched of the oxide, right? So you can see here the rate was different, 0.025, here 0.03. So these two things, rate and time, will be calculated or will be decide how much thickness should be etched or deposited. So in the next line they are forming EP layer. So this was the just for buried layer formation. Now they are going to form the epitaxial layer. Deposit material silicon. In silicon material they are going to deposit silicon material, basically type isotropic, time 1, rate 4, arsenic with arsenic concentration 1E15 per centimeter cube, diffusion temperature 1100 degrees Celsius, time 60 minutes. So they are going to diffuse the silicon material, deposit silicon material for this time at this rate, and with arsenic concentration of this, and they are going to perform diffusion process for 60 minutes, 1 hour at 1100 degrees Celsius. So these all fabrication steps is going to be performed and going to save in this file, structure TDR and node vertical NPN1. So if I show you till now how the device look like, let's explore more, then I will show you. So the final profiles. So now they are using the command like set PLX list total boron concentration, total SB total, that is antimony total concentration, arsenic total concentration, phosphorus total concentration, and write PLX node buried PLX y at y equals to 5, means somewhere here, right? Y equals to 5, they are looking these concentrations, right? Okay. So after doing this, now they are forming the sinker beginning of 2D problems. So for that they are going to refine the silicon minimum at 0.20 and maximum 326. So these are the just a location where the refinement box should be. So refinement box in silicon, like if I go through these lines like 0 to 20, so this is our 0 and 20 is here, so somewhere here to this point 20. Okay, wait a minute. So we are going for sinker definition, right? So 0 to 20. So in x0 here, and in y 20. So somewhere here, the point, this point minimum 0 20 will be somewhere here, this point, and maximum is 3 and 26. So in x direction it is 3. So if I go through this, so somewhere here, yeah, it is 3 somewhere here, and 26 is somewhere here, right? So from till here, so 3 maybe here, 2 here, means earlier one box was here and other box was here, means there will be a box like this. If I can show you that box also, let me show. If I have refinement box, yeah, here you can see. So this code, right? Refined box silicon mean 0 20 is here and maximum 26 is here, right? You can see here. So this box is for the refinements box of silicon, right? And they are going to define a finer mesh in this region, because the physics should be solved, right? So x refinement is 0 2.25, y 0 2.25, and y refinement is also 0.25. so in this region the mesh is would be finer. If you want to see the mesh, then I can show you. Like if I just click in it, so maybe there's some refinements, yeah, no, okay, let me build all the message. Yeah, here you can see we have just created a box, refinement box, then we are going to refine it like this. Just we created a refinement box in silicon with these coordinates, and we are refining x refinements and y refinements, and then grid remesh. We are again recreating the mesh. Earlier we have a global mesh, now we are refining in a specific region. So these statements is telling that now after creating these refinements, we are going to deposit material oxide type isotropic, time 1, rate 0.05. then we are going to use photolithography. Mask we will use sinker mask, thickness 1 micron, right? So we want to deposit a material of oxide with using this parameter time 1 and rate 1. This will decide the thickness of oxide that will be deposited all over the surface. Then we are going to perform a photolithography using the mask of sinker that we have earlier decided, and I know I have explained you this segment name sinker, and it was somewhere here, right? Opening was somewhere here. So that's why we are using for this case here photolithography, mask, sinker, thickness 1, right? Now using the photolithography and after the exposure of those lights and removing that photoresist from this region, we are going to do the implantation in this region of phosphorus. Dose 515 per centimeter square, energy 200 kilo electron volt, right? So and strip photoresist. After doing the implantation in this region, we are going to strip the photoresist from all over the region, right? And do the diffusion temperature and do the diffusion process, so that for at 1100 degrees Celsius for 5 hours, so that the dopant of phosphorus may diffuse accordingly or in a good manner in this region, right? So after doing this implantation and diffusion for these commands, we are going to save this file with the name of structure tdr and node vertical npn2, right? npn2. So let's see this file first. So you can see here, so this type of profiling using these deposition, photolithography, implantation and diffusion process, we are getting this type of profile, right? And this is phosphorus dope. So and this is sinker, I mean collector region. We have formed this region. Now after doing this, they are going to perform base region, refine the mesh in the base region before the base implant. So again we are going to create a base here. So for that we are going to make the like this one. We have just created a box, then do the refinement and remesh it, then do those things, implantation, diffusion and those, right? So same thing we are going to for the base region also. So we are going to create a refinement box, silicon 0.02. so for that you come back to here and you can see, if I turn it off and just turn on the refinement box, here you can see another refinement box we have, right? So for base they have created a refine box, silicon minimum 0, 0.2, somewhere here 0 and 0.2, right? And maximum is 1.5, 1.5 somewhere, and 14.4 somewhere here, this point. So this first coordinate is here and second coordinate is here, and they are refining them as 0.1, 0.1, 0.2, right? And this way by refinement. And they are again grid remesh. Earlier mesh was there, but they are refining in this box smaller mesh size, right? After creating this mesh, they are going to use the photolithography and the mask. As we know, we have designed a mask name with base and thickness 1. So use the photolithography, deposit the photoresist, expose using the mask, you expose that area with UV lights, and there will be openings. In openings we can do the implantation of boron dose with this concentration, with energy this, and after implantation we can strip off this photoresist, right? We can remove the photoresist from this material and we can perform the again we will perform the diffusion process at 1100 degrees Celsius for 35 minutes, so that boron dopants can diffuse accordingly, right? So this is the thing. Again we are going to save this structure with TDR name vertical npm3, right? Let me show you that file also. So this is the process. We just created a refinements box, then remesh it, then we perform the photolithography and implantation, then diffusion, right? So that base region can be formed. Okay, after these things, now we move to emitter regions. So again refine the mesh in the emitter region before the emitter implant. Again we need to refine emitter region in this base region also. So let me show you in this section. And for this, as we can see, like the base and hole both region is covered in this refinement window. So the meshing is done. So now we just need to perform the lithography, photolithography. Then we are using emitter mask we have defined earlier, thickness 1. After performing the photolithography steps like exposure of UV light, then developing the exposed area, then after that we are going to perform the implantation in that, and arsenic dose is being arsenic dopants is being used. Dose is 5E15 per centimeter square, energy is 55 kiloelectron volt, and this time we are now to use the tilted tilt is 7 degree, rotation is 0, tilt is 7 degree, right? So tilted implantation we are doing so that channel may form in this region. So strip photoresist. Now after performing the implantation, we are going to strip the photoresist and perform the diffusion at 1100 degrees Celsius for 25 minutes, right? So by this way we can create the emitter region. Let me show you that also, and we are going to save its structure in npm4. So you can see we have created emitter, base and collector region, right, using these command lines. In the final so the final properties, they have again set PLX list boron, antimony, arsenic, phosphorus concentrations, and they are again writing right PLX, final PLX and sinker PLX at different location, like final PLX at 5, sinker PLX at 23, right? So in the back end, now these are the front end process, right? We were doing the front end process. Back end, each material oxide type time 1 write rate 0.05 mask contact. For the making of the contact, they are using the contact mass, and they are going to use etch the oxide material that is upside. Like if I show you, let me show you. Yeah, you can see a strip. Yeah, this one, right? This is the oxide all over the region, you can see. Now this is just a blue, I mean black. So this is, that one is the oxide, right? This is now black, we can see. So that oxide is going to be etched according to the mask, contact mask, right? So what will be happen, the contact, for we have designed the mask for the contact region, right? Somewhere the opening will be in this, somewhere opening will be here, and opening will be here. So that will that contact mask will going to perform, right? Then after that, reset the M goals parameter to lower mesh requirement above silicon, and grid set normal growth rate. Again, this is the mesh things. And after etching the oxide, we are going to deposit material all over the surface, right? So for that, deposit material aluminum type isotropic, time 1 rate 1, right? With this time and rate, there will be some thickness, and aluminum material will be deposited all over the surface. After depositing the aluminum material, we are going to etch the aluminum material using the mask metal, right? So what will be happen, using that metal mask, some part of this region will be get etched, some part of this region will be get etched, some part of this and some part of this region will be get etched, and the electrode will be formed. Let me show you in the final, like this, right? You can see these are the contacts, and these are being growth by using this deposit of material and etching of the material aluminum, and it is being NPN 5 shapes. So this is all the whole process of simulation of the NPN transistors. I hope you learn from this tutorial. Thank you so much for watching.